This is the second section of chapter 3, which is methods in calculus, and here we look at the mean value of a function. Now we can think of the mean value of a function as the average height of a function. So the average or mean height of a function. Okay, so what does that look like? Okay, so let's draw a function like this, and so this will be x here, this will be f of x, y basically, and let's say I've got a function that goes like this, and I want to find the average height of that function between some limits, and let's call those limits a and b. So by looking at that, I can see the average height might be something like this. Yeah, so that green line represents the average height of that function. Now the notation we use, so whatever that value is there, that would be the mean value of that function. So it's a number. So I'll just write that down here again. So just a function with a little bar on the top, f bar. So we use that little bar sign when we talk about the mean of something. And I suppose we want to work out, well, how do we work out what that mean value is? Well, let's say I've got this area here, and I work out that area. I mean, the way we'd work out that area is we would use integration. Okay, so that area is represented by integrating that function between those limits. And what I have down here at the bottom is the width of this, basically this area. So here, okay, let's write this down. B minus A is the width. So width equals B minus A. So if I take the area of something like this, so let's say we've got a shape like this, and the top varies, the top sort of can do what it likes. And I know what the width is here, and I've got the area. Well then, if I do the area divided by the width, I get this average height. I basically get the mean height. So transferring that then into the notation we're going to use, the mean value of a function, so that's just f bar like that, is equal to, well, we're dividing by the width, so that's why we do 1 over b minus a times by the area between these limits. Okay, let's take this out of the way, don't need that anymore. And that's the important bit. So this gives us this mean value of a function. Okay. Now, next thing we're going to look at is doing transformations on the original function. Okay, so we'll do like a little table. If we do a function here in the first column and mean value in the second column, and we'll talk through each one. So let's say the first function we do is, or the first transformation we do is one which is the original function plus k. Now what does that do? That moves the original graph up by a value of k, or down by a value of k. Now what's going to happen to the mean value? Well, the mean value will also just increase by k. Let's write that a bit bigger. So if we add k to the original function, the mean also increases by k. So if we have 1, we have the original function and the original mean, we can work out the new mean basically by just adding k to the original mean. Okay, let's say we've got another transformation, which is we take our original function and we multiply it by k. Now what does that mean? That means that the graph is going to stretch by k in the y direction. Now since the mean value is basically a value of y, what happens to the mean? Well, that's going to also get multiplied by k. So think of, I don't know, imagine that this mean value here was, I don't know, 10. And we took our original function and the transformation was 3 f of x, which means basically this graph is going to stretch by 3 in the y direction. So instead of this mean value being 10, it's going to get stretched up by a factor of 3. The mean value will be 30. So if the original mean was 10 and k was 3 stretched by 3, then the mean gets multiplied by 3. So that's the second transformation. Let's look at another one. So let's say we've got negative f of x. Now let's think about what this does to a function. So this transformation reflects a graph in the x-axis. So this is a reflection in the x-axis, and when we reflect a graph in the x-axis, so if we use this example, this mean up here is just going to get flipped to the other side of the x-axis down here. So a positive mean value, whatever that number is, becomes the same value but negative, because that mean will flip from this side down to the other side and become a negative. So all we need to do is, if we've got the mean of f of x, then it will be negative the mean of f of x. Okay, so all of these are based on the fact that when we have our original function, the mean of that function is this f bar. Now what about the other transformations? So other transformations are could be f of negative x and f of kx. So let's think about these and see if these still work. So if we look at this one, what this will do, it will reflect a graph in the y-axis. So this is a reflection in y-axis. Now what happens is the interval that was a and b, if you reflect a graph in the y-axis, the interval changes. It's not a and b anymore. In fact, the interval would be negative a and negative b. So we can't use the rules that we had for the other transformations. Okay, so this is what will happen if you reflect in the y-axis, the interval changes. And then if we do this transformation, which is a squash in the by k in the x direction, like that, or dividing by k, again the interval changes. So an interval for the original function, which was a and b, if you squash by a factor of k, then actually the interval now is a over k and b over k. Okay, now because both of these transformations here change the interval, we can't use the same rules as we did for these transformations, because with all of these the interval doesn't change. All that happens is the mean value changes. The mean value will either get something added to it or something multiplied by it, or it just reverses sign. but the x values, the intervals a and b in all three of these transformations remain the same, but with these two they change. Okay, so for these transformations, the rules do not apply. So we can't create the same type of rules in terms of, alright, you just take the original mean and do something to it, because the intervals have changed. Okay, so this one says find the mean value of this function over the interval 2 to 6. So the first thing we're going to do is we're going to write this function, and we'll put the limits in 6 and 2. Yeah, we'll write this function as 4 times by 2 plus 3x to the power negative a half dx. Now this function has this pattern, so k times f dash of x times by f of x to the power n. So if we want to integrate something like that, then we know it's going to become f of x to the power n plus 1 over n plus 1. So our first job is to get this function to look exactly like this. So n would be negative a half in this case. Now to get this function to look like this needs to be f dash of x. So this needs to be f dash of x. So if this is f of x, f dash of x needs to be 3. So I want a 3 there, which means I'm going to play around with the constant to make this a number 3 here, but put the right thing to multiply by, so it still makes 4 when it's all multiplied out. So let's write down what number we want. So I want 3 here. Now obviously, as I sort of just said, you can't just change the numbers and make it a different question. By putting 4 over 3 here, then this still multiplies out to give me 4. So what I've done is play around so it gets exactly in this form, so then I can get this straight away without having to differentiate it afterwards and just check to see whether I need to make an adjustment. So that'll be 4 over 3 here, and then f of x is 2 plus 3x to the power n plus 1, so that'll be a half, divided by n plus 1, so divide by a half, and the limits are 6 and 2. So by doing this, it just makes the working a bit quicker. So I've got 4 over 3 outside, so we're just going to tidy this up a bit. So I've got this 4 over 3, which I need to divide by a half, so we'll do that. So 8 over 3, which I can write outside the brackets, like that, taking the constants outside. And then the power half, we'll write that as square root 2 plus 3x. It just means I can probably write the answer in exact form, because the calculator may convert it to a decimal. It's better to give it an exact form. So 8 over 3 times by, it's going to be the square root of 2 plus 3 times 6 minus square root of 2 plus 3 times 2. So still the 8 over 3 there. Now this will become root 20. Going to be a 20 there, minus, and then this will become 6 root 8 from right. So now we do the mean value. of the function, so the mean value, which is this f bar, is going to be equal to, we want 1 over the width, so 1 over 6 minus 2, basically a quarter of what we've just worked out here, 8 over 3 root 20 minus root 8, and we just simplify it, so you can probably do that on a calculator to see what we get. My calculator gives me 4 root 5 minus 4 root 2 over 3, which I'm guessing you could factorise out the 4's and write that as 4 over 3 root 5 minus root 2. And you'd probably only simplify it and put it like that if the question said give your answer in this type of format. So the question might say give your answer in the format, I don't know, 4 over a times by root b minus root c, where a, b and c are integers. So that's probably the only reason you'd carry on and do that, but this here is fine. Okay, so this one we need to show that the mean value of this function here is given by this over these limits. So your first job is going to be, well, how are we going to integrate this function 4 over 1 plus e to the x dx with these limits of log 6 and log 2. And often in these questions the hardest part is working out how to integrate. Well, it's not going to be integration by parts, it doesn't fit any pattern, so I can use the reverse chain rule, and if that's the case, then always go for substitution. Now when you do your substitution, let's write this down. So if we were to use substitution, we could either make u equal to e to the x, or we can make u equal to e to the x plus 1, and that's the method I'm going to use. Okay, I think in the book they use e to the x. It doesn't matter which way, you'll get the same answer. Or there's another way you could do it, and that's by starting by multiplying everything by e to the minus x. Now I'm not going to use this method because it may not necessarily occur to you to use this in the exam, but I'm just going to show you what's going to happen. So if we take this 1 plus e to the x, and we times everything by e to the minus x, I'll have 4 e to the minus x. Let's actually write down what we're doing here. So we're timesing the top and the bottom by e to the minus x. So that will give me 4 e to the minus x over e to the minus x plus 1, because e to the x times by e to the minus x is just going to be 1. So actually what we'll be trying to integrate, I'll put the 4 over here, is e to the minus x over e to the minus x plus 1. Then you still need to do substitution, so you could let u equal e to the minus x plus 1, or u equal to e to the minus x. And then if you do that, let's say I use this one here, I made u equal to e to the minus x, then I would end up with u over u plus 1, and then obviously my dx I would need to change as well. So du dx in this case, if I differentiate this, would be negative e to the negative x. So I would have dx equal to du over negative e to the negative x, which is basically like negative u, isn't it, minus u. Okay, so that is an option, but as I said, I'm not going to use this because if you went to exam, this may not occur to you to do it this way. I've just started it off. You can maybe finish it off to see what happens. You'll see that the u's cancel out. Yeah, the advantage with this way is that you don't need partial fractions. When we do this way, you'll see that we're going to need partial fractions. So yeah, we're going to do this by substitution, and that means we need to substitute the limits, and we need to substitute the dx and anything else that's got an x in it. So let's start with the limits, and let's use the substitution. As I've said, u equals e to the x plus 1. So if we start with the limits, then the limit of x equals log 6 becomes a u limit of, well, basically all we do is substitute our x for x here, so it becomes e to the log 6 plus 1. So u equals e to the log 6 plus 1. So that's going to be 6 plus 1, so u equals 7. And then if x equals log 2, the other limit, then u is going to be equal to e to the log 2 plus 1, which becomes 2 plus 1, which is 3. So that will be my limits. And now we differentiate as well. So u equals e to the x plus 1. So du dx is just e to the x, which means that dx equals du over e to the x. Okay, now e to the x is u, isn't it? So you could say that dx equals du over, well, actually not over u. Let's just go back to here. So u minus 1 equals e to the x. So u minus 1 equals e to the x. So this bit at the bottom here, e to the x, is the same as u minus 1. So I'm going to write this as u minus 1. So one of these two may be useful. Yeah. It's probably this one that I'm putting the box around now that we may have used, but you'll notice that we need to get rid of the e to the x. So we'll keep that there. And let me highlight the other things we're going to use, which are these limits now of 7 and 3. Now remember, when you do integration by substitution with limits, once you've substituted the limits, you don't need to substitute back. You just work out what you can just evaluate it. Right, so let's get everything changed. So log 6 becomes 7. Log 2 becomes 3. The 4 we'll put over here out of the way. So basically we've got 1 over 1 plus e to the x, or 1 over u. Then the dx we would change to, well, let's say you did this in the exam, and then you'll be thinking, hang on, I can't get rid of the e to the x, I'm stuck with it. Well, this is when we look back at what we've got here, and you can say, all right, e to the x, that's u minus 1. So then you'd say 4 limits of 7 and 3, and then we have 1 over u times by 1 over u minus 1 du. So to evaluate this, we need partial fractions. So we'll put the fraction together. So we'll have 1 over u times by u minus 1, and we'll need to write that as a over u plus b over u minus 1. We want to find the values of a and b. So if we make, well, let's write down the full expression here. So we'll have 1 is equivalent to a times u minus 1 plus b times by u. So yeah, let u equal to 1, okay, which will make this disappear. So that means basically b equals 1. B equals 1. And then if we let u equal to, well, it's going to have to be 0 to get this disappear. So that means a equals to 1 equals to negative a. So a equals negative 1. Right, so now the integral becomes 4 and then 7, 3. This is all with the substitution. So I said a was negative 1, so I'll end up with negative 1 over u, and b was 1 plus 1 over u minus 1 du. Now, since in both of these the top is the bottom differentiated, apart from that little minus there which we can deal with, then it's log of the bottom. So this will become, mustn't forget the 4 here. So the first one will just become minus log u. Yeah, if it was just log u, it would be 1 over u, but we need that minus there as well. And then plus, and then log u minus 1 with our limits of 7 and 3. So the next step now is just to substitute in the 7 and 3. We should get what we're required, which is this thing here. That's what we're trying to get to. Right, so 4 times by negative log 7 plus log 7 minus 1, so that's log 6, minus negative log 3 plus log 3 minus 2, sorry, 3 minus 1, which is 2. So let's tidy this up. So we've got 4. Basically log 6 minus log 7. So that's log 6 over 7. Put it together. So log 6 over 7. And then minus. And then the second bracket here, log 2 minus log 3. So that's log 2 divided by 3. So that's log 2/3. So the bit in the brackets here, log 6 over 7 minus log 2 over 3. So that's going to be the log of 6/7 divided by 2/3. And 6/7 divided by 2/3 is 9 over 7. So this becomes 4 log 9 over 7. Now, we now need to work out what the mean value of the function is. So that's going to be 1 over b minus a, so 1 over log 6 minus log 2 times by 4 log 9 over 7. Now this bit here, log 6 minus log 2 is the same as log 6 divided by 2, which is log 3. So we're basically dividing by log 3. So the mean value is going to be 4 log 9 over 7 divided by log 3 as required. So that's going to be our answer for the first bit of the question. Right, now going on to part B, you might want to pause the video because I'm only going to keep this answer here because I need some space to do parts B and C. So part B here says use your answer to part A to find the mean value over the interval of the original function f of x plus 4. Now we know what the rule is already because we've gone through that on the first slide, but we're actually going to go through it because it says that we need to find it rather than just add 4 to our previous answer. Right, so if we're going to be integrating f of x plus 4 over the same interval of log 6 to log 2, that's going to be the same as doing log 6 to log 2 of, what was the original function, 4 over 1 plus e to the x plus 4. And actually, rather than put that all as one function and then having to integrate it all from scratch, let's use our answer for this part and say, right, let's add the integral of 4 from log 6 to log 2. That's going to be much easier because we already have an answer for this part, don't we? Yeah, we already know that that is 4 log 9 over 7 over log 3. So that means all we need to do is to work out this part, and that should be fairly easy to do. So let's look at that. So let's say consider this integral, the log 6 log 2 of 4 dx. Now I could take the 4 over to the other side, but this is so straightforward. 4 will become 4x. Now this, when I integrate it, so I've got log 6 log 2. So then I will get 4 log 6 minus 4 log 2. And I could simplify that by saying 4 lots of log 6 divided by 2, so that's the same as this, plus a minus, so just get 4 log 3. Okay, so that's that part. So then the total area, so the actual value of this, log 6 log 2, 4 over 1 plus e to the x plus 4 is going to be equal to this 4 log 9 over 7 over log 3 plus 4 log 3. So the mean value of this new function, so mean value of f of x plus 4 is going to be 1 over the interval, which is log 6 minus log 2 times by the area, and that is all of this, 4 log 9 over 7 over log 3 plus 4 log 3. Now I've just realised I shouldn't have divided by log 3 here, otherwise I'll end up dividing by log 3 again, because remember this was the area here, and then when we divided by log 3 we got this, yeah, the mean height, the mean value. So I'm going to take the divide by 3 out, that shouldn't be there. I want to divide all of this by log 3. Yeah, I don't want to divide by the width twice. So if I do that, I will get 4 log 9 over 7 over log 3 once I've divided by the width. Then the second one, I'll end up with 4 log 3 divided by log 3. Okay, so we'll just end up with like what the original area is, which was that, or the original, sorry, not the original mean value plus 4. So I'll just put here, i.e. the mean value of f of x plus 4, yeah? And that was one of our rules, wasn't it? So because we know the rule, we could have, if it just said use your answer to part A and we know the rules, you could say, right, let's just take this mean and add 4 to it, and we could get straight to this. But this is just showing us that this process does work. So just briefly going back over what we did, we wanted to find the mean value of the original function plus 4, which is this, the original function there plus 4. We split the integral up, so it's the area of this plus the area of the 4. We worked out this area here, which basically just becomes 4 log 3. So the total area of this is going to be the original area plus 4 log 3, which is here. We divided by the width, the interval log 2 minus, log 6 minus log 2. That gives us this, and we end up with the original area, which is here, plus the 4. Now part C says, using geometric considerations, write down the value of negative f of x over the same interval. Well, what does negative f of x do? Well, that's a reflection in the x-axis. Okay, so since negative f of x is a reflection in the x-axis, okay, the mean value has the same value but the opposite sign. Yeah, so if it's got the same value and it's got the opposite sign, what that means is that the mean value of negative f of x so the mean value of that is basically equal to the negative value of the mean, which means, let's put the answer for C up here so I don't have to rub anything out. It means basically just putting a negative sign in front of the mean value for a function, which is going to be a negative sign in front of 4 log 9 over 7 over log 3. So it's just going to reverse the sign there. Okay, so that will be our final answer for part C. You should now be able to do exercise 3B on pages 61 to 62 of the textbook. So just as a quick recap, this mean value of a function, f of x is basically like the average height of the function, is given by finding the area between the interval a and b and dividing by its width. So this would be the area of the function, which gets divided by its width, and the notation for that is this f bar. Now if we take our original function and we increase it, it moves up by k, then the mean value of that function also increases by k. If we take our original function, we multiply it by k, then the mean of that function, or the mean value of that function, also gets multiplied by k. And if we reflect our original function in the x-axis, then the mean value of that function just reverses sign. It has the same value. And remember that we can't use these transformations for functions like this. Because what these do, these change the interval. So the interval gets changed, whereas the interval on these ones remains the same. Okay, so these are true for the interval from A to B.